Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and in the Masterstroke series today I am going to discuss about semiconductors. 4 questions historically came from this chapter, but there are some changes we can expect because some concepts from this chapter which were very popular in the KCET exam category that are now deleted. For example, one is Zener diode. There will be no questions related to Zener diode from this chapter. So if you are practicing questions for Zener diode, that will not be coming in your KCET exam. Okay, secondly, logic gates are also deleted. There will be no questions from logic gate as well. So only few scopes, few remaining scopes, whatever is there, that we are going to discuss. It will be slightly theoretical heavy because all the numericals and interesting questions are now deleted. So it will be little theory, and without any delay, let's start with the session today. So first we will see what are the list of important concepts as usual. So first is semiconductors and band theory. We can expect at least one questions coming from the band theory concept. Second will be classifications of semiconductor: intrinsic, extrinsic, p-type, n-type. P-type and n-type is part of this classification, but still it is important to know about it. Then p-n junction diode, okay, very important concept. And lastly, biasing of a diode. How can you bias a diode? Forward bias, reverse bias. And application part, we will learn about rectifiers. Okay, so basic example of rectifiers and what type of questions that might come also we will going to discuss in this session. So let's see. So first is conductivity. Okay, metals and conductors, they possess very low resistivity, or they are also considered high conductivity. So resistivity is given by rho and conductivity is basically reciprocal of that. Okay, so if the conductivity is low, then resistivity is high. If resistivity is low, conductivity is high. So for example, metals have very low resistivity but very high conductivity. Okay, second, and the range is given here from 10 to the power of minus 2 to 10 to the power of minus 8 ohm per meter. So this is the resistivity. Okay, and the conductivity will be, as I said, it will be reciprocal of that. So it will be 10 square to 10 to the power of 8 ohm inverse, meter inverse, right? Now insulators, they have very high resistivity or low conductivity. They do not conduct at all. For example, wood, okay, wood or plastic, they are basically considered to be insulators. Insulator means they do not conduct electricity. Okay, again, it's as you can see, its resistivity is very high, 10 to the power 11 to 10 to the power of 19, and conductivity is reciprocal of that. So 10 to the power of minus 11 to 10 to the power of minus 19. So they generally do not conduct electricity at all. Okay, and semiconductors are very interesting. We will discuss about this part in this lecture mostly. We have learned this in our current electricity chapter about these 3 types of materials, right? But what is semiconductors? We said we will discuss in our future lecture, right? So in this case, they have resistivity or conductivity intermediate to the metals and insulators. So both cases, their resistivity is also intermediate, their conductivity is also intermediate. Okay, so they are not as high, as good as metals, and they are not as bad as insulators. Okay, so they are in between, and we will see how we can apply them in our advantage. Okay, so let's see one question from KCET 2022. So there are this type of questions are very much expected. The resistivity of a semiconductor at room temperature is between. So they asked you resistivity, not conductivity. Okay, 10 to the power of minus 2 to 10 to the power of minus 5, 10 to the power of 6 to resistivity. If this is very high, as you can see, very high means they are insulators. This is also insulator. Either 10 to the power of minus 2 to 10 to the power of minus 6, or 10 to the power of minus 3 to 10 to the power of 8 ohm meter. Okay, so let's see once more. So as you can see, the resistivity is 10 to the power of minus 5 to 10 to the power of 6. This is the average range. Okay, so So in this, from the given observation, from the given range, we can say, because it is ohm meter, so now you have to understand that it is in ohm meter. Okay, ohm meter was the unit. Now if you take it in centimeters, that is, you have to multiply with 100. So 10 to the power of minus 5 will become 10 to the power of minus 3, 10 to the power of 6 become 10 to the power of 8. Okay, so this is very interesting because they have changed the unit. So you might feel that, okay sir, none of the answers are matching, but yes, it is matching, because ohm centimeter means when you are converting into ohm meter, it will become 10 to the power of minus 5 to 10 to the power of 6. Okay, so you have to divide it by 100 to convert it into SI unit. The range that range is important to remember, at least for conductor and semiconductor you have to remember. Okay, other than that you don't need to remember. Insulator you don't need to remember. Any high value is suitable for insulators. Okay, but semiconductors are very interesting. So it is starting at 10 to the power of minus 5, ending at 10 to the power of 6 ohm meter, and answer is option D. Okay, this is the range for generally some weak conductor. This is semiconductor. Okay, now let's move on. As you know that if you want to score well in your upcoming KCET 2025 exam, then you must purchase Abhyas KCET test series, where we are giving you total 35 tests. Out of that, 4 tests are free and 31 are paid. And don't wait till last moment, purchase right now. You will get 1498 is the current price. So before the price goes up, you have to purchase it. Okay, a lot of students already have purchased, so don't wait till the last moment. Purchase it now and know your progress, how you are doing against all other students who are taking up this test. Okay, now band theory. What is band theory? Inside the crystal, each electron has a unique position. Because of this, each electron will have a slightly different energy level. These different energy levels with continuous energy variation form what we called energy bands. Okay, so crystals of each electron are not same energy level. Okay, even though we say that energy of a single orbiting electron is same, but when they are forming a crystal, there is a slight energy variance. Okay, so all the electrons inside the crystal, they do not possess the same amount of energy, even though they are at the same level. Okay, for example, if I say we know that there is a nucleus, we have K, L, M, like that. Okay, so all the electrons, suppose this is a basic electronic configuration. Okay, so suppose this electron, this is a valence electron, for example, just take it. So this is a valence electron. Now what will happen to this electron? Now for a given atom, energy is fixed, right? Energy is fixed. But when these atom constitute a crystal, each electron, even though they are all of them at the same level, okay, same orbit, same orbital, their energy still is not same. Okay, so inside a crystal there is a different geometry, different logic comes into play. We are not going to in that detail, but you can say that all the electrons do not have the same energy level. Okay, so their energy level varies based on where they are inside the crystal. Okay, so these different energy levels with continuous energy variation from what we called energy band. So when we combine all the energies from all the electrons, they will vary the energy level. So that is combined together, all the electrons in the same level, then we call them energy bands. Okay, the energy band, which includes the energy levels of the valence electrons, is called the valence band. The energy band above the valence band is called conduction band. So if you consider only the valence electrons are whatever total energy, or you combine all the energy levels, they stack together. Okay, so one or more electron can possess the same energy, but total all, suppose there are 10 to the power of 23 electrons. electrons. Okay, that is the Avogadro number. So I am saying 1 electron from one atom. We have 1 mole of substance, 1 mole of atoms. Then we can say that 10 to the power of 23 electrons. Obviously they will not have, not all of them have different energies. There will be a lot of electrons, they will possess the same energy, but 10 to the power of 23 electrons, that is a huge number. Definitely they will vary the energy, and the total energy of the valence band, valence valence electrons, the total energy of that, whenever we represent them, we call it valence band. If some electrons will go up in the higher energy level, and the total energy gap between them is called conduction band. Okay, so conduction band is one level, just next level of valence electron. Okay, now the gap between top of the valence band and the bottom of the conduction band is called energy band gap, or EG. So so we generally represent them like this. So this is the valence band, this is conduction band, this is valence band, this is conduction band. Okay, energy one level up. There are other energy levels in below also, but we are not interested in that. In semiconductor physics, only valence band and conduction band is sufficient. Okay, now the energy gap. So whatever is the energy gap, so top of the valence band and bottom of the conduction band, that is called energy gap, EG, also sometimes called forbidden energy gap. Okay, forbidden energy gap. Okay, so it may be large, small, or zero depending upon the material. Okay, so the top of the valence band, bottom of the conduction band, remember that, and it can be different for different elements. Let's see. So based on their gap, energy gap, we divide them into 3 different categories. First is obviously conduction band and valence band overlapping. So as you can see here, conduction band, wherever conduction band is ending, okay, and wherever valence band ending, they have a common area. So they are overlapping. Conduction band starts here, it ends here. Valence band starts here, it ends here. But there is a zone of overlapping happening. Okay, and in this case the band gap is 0, almost equals to 0. So for some materials it may be close to 0, but most of the metals it is 0. In this case, the resistance of such material is low or the conductivity is high. Such materials are called conductors. So in terms of band theory, conductors are those, for them the bands overlap with each other. Okay, bands overlap with each other. Next is large band gap. So band gap is higher than 3 electron volt. Remember this threshold. Okay, band gap is greater than 3 electron volt. So there are no electrons in the conduction band. Electrons, as you can see, in conduction band is empty. Okay, no electrons are there, no electrons in the conduction band, and therefore no electrical conduction is possible. This is the case of insulators. So they are insulators. If band gap energy is greater than 3 electron volt, then they are called insulators. Next is finite but small band gap. Band gap is less than 3 electron volt. Very, very important. So if the band gap is less than 3 electron volt, there is a chance that higher temperature, as the temperature increases, the band gap decreases. Okay, some electrons will go to conduction band and give rise to conduction. So what is the meaning of conduction band, by the way? If electrons are present in the conduction band, then only the material can conduct electricity. Okay, so if there is no electrons in the conduction band, then it will not conduct any electricity. So to conduct electricity, it must have some electrons present in the conduction band. Okay, because of the small band gap, the room temperature, some electrons from valence band can acquire enough energy to cross the band gap and enter the conduction band. These electrons, though small in numbers, can move in the conduction band. Hence, the resistance of the semiconductors is not as high that of the insulators. So, as you can see, this is the case of semiconductors. So, in case of semiconductors, some electron, when they get sufficient energy, they can escape the valence band and they can move to the conduction band. So, you can imagine this is your house, this is your playground. Okay, so by sneaking past your mother, you can go to the playground, play cricket or chat with your friends, etc. But when you are during the exam, obviously your parents won't allow you to go outside, so that time band gap increases. Okay, so that time it is higher, no escape is possible. But when there is relaxation, there is no college is going on, okay, and you are on a holiday mood, you can go and play cricket whenever you want. Similarly, like that also semiconductors behaves like the same way. When there is a lot of energy available, they can escape to the conduction band and conduct electricity. Okay, electrons' sole purpose in this theory is that they are born to conduct electricity. That is their main job. Okay, they do other things also, but their main job is to conduct electricity. Now, how they can do that? Only if they are allowed to leave the valence band, go to conduction band, then only they can conduct electricity. Okay, now in detail about semiconductors, we have how many types of semiconductors? Elemental semiconductors, silicon and germanium. Okay, so they are elements. Elemental means elements. Okay, so they are forming in an element form. Silicon and germanium, they are naturally occurring semiconductors. Compound semiconductors, so sometimes you will find some compounds, they also behave as semiconductors. For example, inorganic. So in the compound semiconductors, there are two types, or inorganic and organic. So cadmium sulfide, gallium arsenide, cadmium selenide, indium phosphate, etc. are the examples of inorganic semiconductors. Okay, and organic semiconductor are, you can remember some names, not necessary. Anthrans, doped thiamines. Okay, they are the examples of organic semiconductors. But in our real life, more than inorganic or elemental semiconductors, elemental semiconductors obviously have their uses, but organic semiconductors are more common and we see them in everyday life. Okay, where do we see them? Let's see. Organic polymers also there, polypropyl, polyaniline and thiophane. Okay, they are examples of organic polymers. Okay, now organic polymers based semiconductors are used in displays, mobile display through which you are seeing this video, or the laptop display or the tablet display, wherever you are watching this video on, that is basically based on organic polymers. Okay, so OLED, AMOLED, here this O basically means organic light emitting diode. Okay, organic light emitting diode. Okay, so this O basically represents organic. Okay, even this video is recorded in the smart board. Smart board is also based on OLED. Okay, and it is recorded also in OLED. So without OLED, this video was not be able to possible to record and give it to you, right? Interesting. Now let's move on. So naturally occurring elemental semiconductors, gallium, germanium and silicon, are called intrinsic semiconductors. So intrinsic semiconductors means elemental semiconductors. Okay, germanium and silicon. The crystal structure, also called lattice structure, of silicon and germanium are shown here. So this is the obvious crystal structure, how they form the crystals. So crystal means they are in a stable format, stable orientation. So as you can see that a silicon has valency 4. So valency 4 means it requires 4 other silicon present near it so that it can create a covalent bond with them. So here as you can see, this silicon, this is suppose our central silicon, our hero, he has 2 silicons on his right and left and another 2 top and bottom, and they are making covalent bond like this. Okay, now if you are not accustomed to this, you can show this way as well. If you want, you can imagine them like this as well, like we used to do, right? This is how the electron is being shared. So 2 electrons are shared amongst them. This is a single bond, okay, not a double bond. So sometimes this gives you a false implication that it's a double bond. It's not a double bond, it's a single bond. Okay, so this single bond, in this single bond they are sharing 2 electrons. Similarly here also single bond, here also single bond. So the silicon is sharing its electron with 4 other silicon. One silicon is sharing with other 4 silicons, and this is a very long structure. Okay, and everything is oriented like this. This is a very small area, so if you zoom in you will see this. This is a very structured configuration, right? Now we know that silicon and germanium have 4 valence electrons. Every silicon and germanium atom share one of its 4 valence electron with each of its 4 nearest neighbor atom. Nearest neighbor means whoever is sitting next to it. So imagine this is a classroom, so you are chatting with whoever is your left, whoever is your right, whoever is your front, whoever is your behind. You are saying that okay, today we want to go to play cricket. So he is saying no, I have tuition classes. He is saying no bro, I will go to play cricket. So like that you discuss. Right, there are a lot of other things also you discuss, but I just give you one example. These shared electron pairs are referred to as forming a covalent bond or simply a valence bond. Okay, so either you can call them a valence bond or covalent bond. So they are forming covalent bond with each other, they are stable, they are happy. Okay, now we are talking about holes. Thermally excited electrons leave the bond and creates a vacancy with the effective charge. Okay, this vacancy with the effective positive electronic charge is called a hole. Okay, the hole behaves as an apparent free particle with effective positive charge. In intrinsic semiconductors, the number of free electrons Ne is equal to number of holes Nh. Okay, that is Ne equals to Nh equals to Ni, where Ni is called intrinsic carrier concentration. Okay, we learn one formula based on that. There was a question in this year's PU exam, and maybe one more question you will get in your KCET exam as well. Okay, so the total current I in this is the sum of the electron current IE and hole current IH. So whenever you see a hole, okay, so holes are basically when somehow one electron leave its place and leaves behind a hole. So for example, one of your friend did not came to college today, and you said no one will sit here, it will remain empty, but during the class your teacher came and it threw you back, you went there, and again some other teachers came, they shifted some other student there. So all throughout the college day someone was coming and sitting at that place, right? So it is like a conduction. So same thing happens in case of semiconductor as well, and total current in the circuit is basically due to electron current plus hole current, both are moving. Now extrinsic semiconductors, from here things get interesting. So the conductivity of an intrinsic semiconductor depends on the temperature, but at room temperature its conductivity is very, very low. So basically that says that if you design a semiconductor chip, okay, computer chip that based on elemental semiconductor. Suppose you made a chip based on elemental semiconductor, silicon or germanium, and now you want to design a mobile phone using silicon and germanium, suppose. So what is the primary condition? Normally it will not conduct, so you have to put it inside the heater to make it work. Right, but that is not possible. If you heat it too much, your display will burn, your other circuit parts will burn. So you cannot create a chip using a elemental semiconductor. So what you have to do? You have to do something about it. So as such, no important electronic devices can be developed using these semiconductors, right? So as I said, now to develop something, what you have to do? Hence there is a necessity to improving their conductivity. So we have to improve the conductivity of elemental semiconductors. Okay, this can be done by making use of impurities. Okay, so if you put some impurity in the crystal, then definitely it will improve its conductivity. When a small amount, say a few parts per million of a suitable impurity is added to the pure semiconductor, the conductivity of the semiconductor is increased manyfold. Okay, so if you add some impurity into the semiconductor, then its conductivity increases. That means it becomes a better conductor. Okay, and such materials are known as extrinsic semiconductors or impure semiconductors. So extrinsic semiconductor means impure semiconductor. So basically it's a pure semiconductor plus impurity. Okay, so extrinsic semiconductor means pure plus impurity. Okay, this is the meaning of extrinsic semiconductor. The deliberate addition of desirable impurity is called doping. Okay, and the impurity atoms are called dopants. Such materials is also called doped semiconductor. Okay, so everything doped semiconductor, impure semiconductor, extrinsic semiconductor, they are all same. There are two types of dopants used in doping: the tetravalent silicon or germanium. Okay, pentavalent so there are two types of dopants that we use for silicon and germanium. Okay, like arsenic, antimony, phosphorus, they are pentavalent, and trivalent. Pentavalent means valency 5. Okay, so if you add 5 valent dopant into the tetravalent silicon and germanium, okay, their conductivity changes. Similarly, trivalent, so either one more valency or one less valency. Okay, you cannot dope with anything. You have to dope either. So silicon has a valency 4. Okay, so either you have to dope it with 5 or you have to dope it with 3. Trivalent example: indium, boron, aluminium, etc. Okay, for number of holes NH and number of electrons Ne, the relationship is NeNH equals to Ni square. So this is the formula based on which you received one question in your PU board, as I said in the previous part. So what is Ne? Ne is number of electrons. Okay, NH is what? NH is number of holes. What is Ni? Ni is intrinsic carrier density. So in case of intrinsic carrier density, Ne and NH was same, and we denoted that with Ni. So if it is intrinsic, so that will be Ni, but when you dope it and then you try to calculate Ne and NH, then they are related through this formula, this small formula but very important formula. Okay, now let's see N-type semiconductor. So this is obtained when silicon or germanium is doped with the pentavalent impurity. So if you dope with pentavalent impurity like phosphorus, arsenic, antimony, etc., you get a N-type semiconductor. The extra electron in the pentavalent atom can be made free and can participate in the conduction. Okay, here the ionization energy required to set this electron free is very small, and even at room temperature it will be free to move. So once you have doped it with a pentavalent material, the extra electron you have freed one electron, and that electron takes part in the conductivity, and basically what it says that it improves its conductivity, so it remains a good conductor even at room temperature. Okay, the energy required is 0.01 electron volt for a doped germanium and 0.05 electron volt for a doped silicon to separate the electron from this atom. For reference, 0.72 electron volt for germanium and about 1.1 electron volt for silicon when they are pure. So as you can see that this energy, that is if you want to jump one electron from valence band to conduction band, for germanium you were required 0.72 electron volt, whereas for silicon you required 1.1 electron volt. But if you dope it with the pentavalent, that energy 1.1 electron volt drops to 0.01 and 0.05 electron volt, which is almost negligible, right? So what you have done, you have made it possible for the electron to jump from valence band to conduction band and participate in the conduction. For n-type semiconductors, we have number of electrons is basically more than number of holes. So majority carrier is electron, minority carriers are called holes. Majority means whoever is higher in number, they are called majority carriers. Whoever is smaller in number are called minority carriers. In intrinsic semiconductor, there is no majority, no minority carrier. Okay, both are same. But in case of n-type semiconductor, the number of electrons are more than that of the number of holes. Now there is a question: what is the sign of a n-type semiconductor? If you touch it, will you get electrocuted or not? Okay, so it is negatively charged, positively charged, neutral, none of the above. Okay, so you have to remember that even though you have increased the number of electrons taking part in conduction, the overall charge is still neutral. N-type conductor still neutral in terms of charge. Okay, it is neither negatively charged nor positively charged, it is electrically neutral. So based on that, if you see any MCQ, you can answer that like a flash. Let's move on. P-type semiconductor. This is obtained when silicon or germanium is doped with a trivalent impurity like aluminium, boron, indium, etc. Okay, the dopant has one valence electron less than that of silicon and germanium, and therefore this atom can form covalent bonds with neighboring 3 silicon atoms but does not have any electrons to offer to the 4th silicon atom. So the bond between the 4th neighbor and the trivalent atom has a vacancy or hole. Okay, so silicon wants to have one extra electron, but boron is not able to supply that electron, so there is a hole created. That hole attracts other electron towards it. Okay, and because of that, a lot more extra holes are getting created. Okay, for p-type semiconductor, number of holes is definitely more than number of electrons, and again it is electrically neutral. You have to remember that, be it p-type, be it n-type, they are always electrically neutral. They do not have any extra charge. Extra charge is zero. Even though you are getting extra electrons, you are getting extra holes, the total charge still remains zero. Okay, excess charge is zero. Now p-n junction. So p-type and n-type generally are good in conduction, but still they are not as good as a conductor. So what are the use of this? So one of the use of them is p-n junction diode. Okay, there are other types of application as well, but this is the very basic part. Okay, in a p-n junction diode, n-type semiconductor, the concentration of the electron is more compared to the hole. Similarly, in a p-type semiconductor, the concentration of hole is more than that of the electrons due to the concentration difference across the p and n side. So let me tell you briefly how they are formed. Generally there are many ways to do it. Okay, one of the easiest way to take one single silicon wafer. Wafer means the same thing that you eat as a wafer, very thin piece of silicon, but it is not edible. Okay, so you take the wafer and you start adding the dopant. Okay, there are very tiny things are there. From one side you start doping it with the p element, from other side you dope it with the n element. So from this side you are doping with the trivalent, from this side you are doping with the pentavalent. Okay, and they are precisely so that they just overlap at a very small tiny portion. Okay, and in your textbook they have given the entire thing was first made p, then from other side, other half they made n. That is also a way of doing it. There are other ways as well, but remember that you cannot make p-n junction by taking a p, taking an n and joining them together. Okay, that is not the way to create a PN junction. You will not get a PN junction like this way. Okay, it has to have from a single piece of silicon or germanium. Okay, very important. So on a single piece of silicon and germanium you have to form PN junction. You cannot individually make P in one silicon, N in another silicon and then join them together. It will not work. Okay, so just for your information, this is just informative. Now, due to the concentration difference across P and N sides, during the PN junction formation, holes diffuse from P side to N side and electrons diffuse from N side to P side. This motion of charge carrier gives rise to diffusion current. Okay, so now P side has more holes, okay, that electrons want, and N side has more number of electrons, that is the P side ones. So they are fulfilling their requirements. So electrons start jumping from this side to whole side, holes start jumping from P side to N side. Okay. When an electron diffuses from N to P, it leaves behind an ionized donor on N side. This ionized donor positive charge is immobile as it is bonded with the surrounding atom. So suppose we have doped a phosphorus. So that phosphorus is giving that extra electron, but when here it is giving that extra electron, the phosphorus is becoming positively charged. Right now that phosphorus is bound to the crystal structure. Okay, it came as a foreigner, but then it forms a bond with the silicon and it gives away that extra electron that it had. That extra electron now moved to the P side. That means on the N side there is a positive phosphorus who is hungry for his missing electron. Okay, so as the electron continues to diffuse from N to P, a layer of positive charge on N side of the junction is developed. So as the electrons keep on moving from negative to positive, you will see that there is a layer of positive charges on the N side. So these are not holes. These positive charges are basically the donor atom that donated that extra electron. Okay, similarly the P side who is accepting the electrons, okay, the acceptor electrons now they are getting negatively charged because they initially was neutral, now they are accepting more and more electrons. So it will get a negative charged layers. Okay, one side, so N type will get positive charge, P type will get negative charge. Okay. Similarly, the holes diffuse in the opposite direction and a layer of negative charge on the P side of the junction is developed. This space charge region on the either side of the junction together is called depletion region, as electrons and holes taking part in the initial movement across the junction depleted the region of its free charge. So there was a battle. So negative army electron, positive army holes, they fought a lot and they died in the field. So this is the field where all of them are dead, no one is moving. So that is why it is called depletion region. Depletion region means it is depleted, everything is gone, all the moving charges are gone. That is why it is called depletion region. Now there is a potential difference in the depletion region. So negative, as you can see, positive side is lower potential, negative side is at higher potential. So there is a potential difference. Okay, it is also known as barrier potential. Okay, the potential difference developed is called barrier potential, and it stops any further mixing of charges. So barrier potential stops any more mixing. So barrier potential is like a flag bearer. He is saying, okay, stop the war, you cannot go, anyone should not go to the field and fight the war. So it is basically stopping the war. Okay, now the thickness of the depletion region is of the order of 0.1 micrometer. Okay, 0.1 micrometer is obviously 10 to the power of minus 7 meter, of the order of 10 to the power of minus 7 meter. Micrometer is 10 to the power of minus 6, 0.1 is there, so 10 to the power of minus 7. An electric field directed from N side towards P side develops. So there is a electric field develops. Okay, obviously N side is positive, P side is negative. So electric field is always from positive to negative. So from n side to p side there is a electric field developed. Due to this field, electrons on the p side of the junction moves to the n side, and a hole on the n side of the junction moves to the p side. Now it is opposite happening. So electric field is developed, so that electric field is trying to convince the electrons who is located in the p side, come to my side, I am positive, and the p side is saying the holes on the n side that okay, come to my place, I am still negative. Okay, so they try to convince each other. The motion of the charge carriers due to the electric field is called drift current, right? We know that drift means when electrons or holes are moving due to electric field, right? In a PN junction under equilibrium there is no net current, that is the diffusion current equals to the drift current. So as soon as the drifting starts place, okay, so the some junction is narrowing down again, and then again diffusion starts place. So diffusion is trying to make it broader, and drift current is trying to make it smaller. So when drift and they are balancing each other, when they are balanced, then at that point of time drift current and diffusion current, they are equal. Okay, so as you can see, electrons are drifting from p to n side, electron is diffusing from n to p side. Okay, holes are diffusing from p to n side, holes are drifting from n to p side. So they are always moving in the opposite direction. So drift current and diffusion current, they are equal in equilibrium. Now let us discuss about semiconductor diode. Okay, semiconductor diode, the same thing that we have studied in our past, that is called a semiconductor diode, PN junction. Now this is the symbol of PN junction. What is the meaning of this? This represents the p side and this represents the n side. Okay, now why this weird particular diagram? So basically we will see that in a while in the biasing part. If current goes from this to this, it will not be blocked. So that is the reason for this arrow. So arrow means current passing from this side to this side, it will not be blocked, it will be allowed to pass. Okay, so if say some current is passing coming from this side, so it will pass. Okay, but whereas if some current is trying to come in this direction, okay, then it will be blocked. Okay, so current will be blocked if they are trying to come from this side. They will see the wall, and it is current, not electron, by the way. Electrons are opposite to that current, right? So here we are talking about conventional current. So if current is passing in this direction, they will be allowed, but current passing from this side, they will not be allowed. Okay, so in this direction current is not allowed, this direction it is allowed. Okay, so a semiconductor diode is basically a PN junction with metallic contacts provided at the ends of the application of an external voltage. So if you see that MCB circuit, we say MCB circuit. What is MCB? Magnetic circuit board. Okay, where you have a lot of chips inserted, some gold linings are there. So they are basically electrical contacts. Okay, so those electrical contacts can connect to you the PN junction diode or whatever components, electrical components are there. Okay, this is a two-terminal device. A PN junction diode is a symbolically represented as shown in the figure. This is the symbol, and the direction of arrow indicates that the conventional direction of current. Okay, when an external voltage V is applied across a semiconductor diode such that P side is connected to the positive terminal of the battery and N side to the negative terminal, it is said to be forward biased. So as I explained that if you connect positive battery here and a negative battery here, okay, so it will be called forward biased because current will be passing through the diode. Okay, if you reverse the battery, current will not flow this through this. That is why it is also sometimes called diode valve. Okay, valve means it allows something to pass only through one direction. Okay, mechanical valves, we have valves in our heart also, so they only allows the blood flowing in the particular direction. It does not allow the blood flowing in the opposite direction. That is the work of a valve. Same as PN junction, it allows the current to pass through only in one direction. That is why it is sometimes also called diode valve. So the direction of applied voltage V is opposite. Now we are discussing about forward biased. Obviously the direction of applied voltage V is opposite to the built-in potential V0. Okay, as a result the depletion region with decreases and the barrier height is reduced. So in this case what happens is that the depletion region, when you apply, so depletion region is, suppose as I said, electric field is in this direction. Now you are applying, this is P, this is N. Okay, so in the barrier this is positive, in the barrier this is negative. Now you have connected positive here and a negative from outside. Okay, now what is happening, this is the barrier potential, barrier electric field, and when you applied the battery, the current is trying to pass in this direction, and that is why the depletion region will be getting narrower and narrower, smaller and smaller. Okay, the effective barrier height under forward bias is V0 minus V. Okay, so as you can see that if you are increasing the voltage, okay, the width is decreasing, and as you are increasing the applied voltage, the barrier potential decreasing, keep on decreasing until it becomes 0 when voltage is more than that value. Okay, so I think that was not mentioned. So V0 by V0 until V is greater than V0. Okay, when V is greater than V0, there is potential difference is 0, barrier potential becomes 0, and it is forward biased, current will pass through the circuit. Now reverse bias, in the reverse bias, when an external voltage V is applied across the diode such that N side is positive and P side is negative. Now what you are doing the reverse of that. So you are making the negative side positive and you are making the positive side negative. So what will happen in this case, the barrier potential obviously will increase because it is supplying more and more positive charge to this side, so they are all accumulating over here, and negative charges are accumulating over here, so the width of the depletion region keep on increasing. Okay, the direction of applied voltage is same as that of the direction of barrier potential, and as a result the barrier height increases and the depletion region widens due to the change in the electrical field. So the effective barrier height under reverse bias is V plus V0. Now in an ideal diode, what is the meaning of ideal diode? Ideal diode means it is an ideal world. In case of an ideal diode, the barrier potential is 0. Okay, barrier potential, normal barrier potential, equilibrium barrier potential is 0. So as soon as you make it a forward bias, it will start conducting electricity. If you connect it into the reverse bias, no matter how much voltage you apply, it will still not allow any current to pass through it. In real diode it does not happen. In real diode what you get is like this graph. Okay, so this, from this graph, if you are given a graph like this and they ask you what is the barrier potential, how to answer that question. So if they ask you that what is the barrier potential in this case, so you can see that the graph was flat up to 0.6. So from this you can say that this is the barrier potential, this much voltage must be overcome by the applied input voltage. So this is the barrier potential, 0.6 volt is the barrier potential in this case. Once the barrier potential is overcome, now as you can see that as you are increasing the input voltage, the current increases significantly and it is in the range of milliampere. Normally for Ohm's law graph, the graph is straight line, and not only that, graph was straight line from starting from origin. This is the normal ohmic graph. Okay, but in this case this is not a normal ohmic graph because the graph is like this. right? So this is non-ohmic conductor. Now in case of reverse bias, if it was an ideal diode, the graph would be flat like this, but it is not happening. Okay, you are increasing the reverse voltage, after certain time it reaches something called a breakdown. Okay, so breakdown means when it starts increasing the current even in the reverse direction suddenly. Okay, there are different regions for that. Zener breakdown was one of the famous breakdown, but that is not there in our syllabus anymore. Even we use the Zener breakdown as our application, but as I said, that is not part of the syllabus. Anyway, breakdown can also be utilized in our advantages way as well. But anyway, so breakdown is basically when the diode is in reverse biased. Okay, now there are two applications. Half wave rectifier, just for your information. Okay, half wave rectifier is, it is only one diode is included and this is conducting in one particular direction. So this is the AC input signal. AC input signal is increasing, decreasing, but when it is increasing, that means this side is positive. Okay, when this is decreasing, this side is negative. Okay, so this is negative, this is positive. Okay, so when this side is positive, other side is definitely negative. When this side is negative, the other side must be positive. So bracket represents the pairs, right? Now positive and negative means diode, this side P side is connected to positive, N side is negative, so it will conduct the electricity. But in the reverse case, when this is positive, this is negative, there will be no conduction of electricity. And if you see the graph, so this is the input voltage, okay, having both positive and negative, but the output voltage only has this. Okay, only half of the input voltage is converted into DC. So this is all of the current, all of the voltage and current are only in single direction. That is, this is why called it is DC. Ideal DC should have been a flat straight line, but you are not getting an ideal DC. It's a oscillating DC. It's varying with time, and it is also have some zero component as well. Obviously this is not ideal. We don't want to use a DC like this. So what we will do, you will have a we'll have a full wave rectifier. So full wave rectifier is where we are converting both halves of the input AC signal into DC. So first, obviously we know that this half, this is positive and this end is negative. This end is always 0. Okay, so now this is positive and this circuit is connected through this load resistance, not to the negative but to the 0 point. Okay, the reference point, we call it a reference point. So now this side is positive, this side is 0. That means P side is in higher potential than N side, so definitely it will conduct in this case. Okay, now in the reverse case, this side is negative and obviously this diode will not conduct. This side is negative, this side is positive. Now if this side is negative means this diode will not conduct. Now this side is positive means the second diode will conduct because it is also connected to the 0. So when this side is positive, diode D1 conducts, and when this side is positive, diode D2 conducts. Okay, so both diode conducting in the separate halves. They do not operate on the same time. They are operating after taking some breaks. Okay, so we have two employees now. Two employees are converting the both halves of the input voltage, and it is a better DC. Obviously it is not as usual as our ideal DC, but still it's a better DC. Now to convert it into a particular better DC, you have to use filters. Capacitor filter, basic capacitor filter is there, but only the diagram was there. Explanation was not part of the syllabus, and different types of filters are also not part of the syllabus. Okay, so there you can use different types of filters, inductor filters, capacitor filters, and there are also different types of filters. They help you to stabilize the DC and give you a constant DC volt. So similar, some expensive filters are used in your mobile phones chargers, so that with the mobile phone charger, what is the role of it? It converts the alternating current into DC, because your mobile phone can only work in DC volt. Okay, your mobile phone, your laptop, your TV, okay, your computers, they all work on DC voltage only, whereas your light, fan, AC, fridge, they can all work on AC. Okay, all electronic devices, they require DC to work. Now that is why there is something called an adapter. Okay, that adapter function is take the AC input and convert it into DC voltage. Okay, so now when they convert it into DC voltage, there is a filter applied inside the desired circuit. So they have a rectifier circuit. Okay, not this simple rectifier, higher version of the rectifier, but the principle is same. And there is a filter circuit. That filter circuit filters this variations, these ripples, into small ripples, and then it stabilizes it to a fixed voltage. Okay, now I hope you enjoyed today's session, and one more question is still left. Let's see that. A full wave rectifier with diode D1 and D2 is used to rectify 50 Hz alternating voltage. The diode D1 conducts dash number of times in 1 second. This is a question from KCET 2023. Okay, so 50 Hz means 50 times a second it is giving you high, and 50 times in a second it is giving you low. Now in the high, that is the maximum point, diode D1 conducts, and the minimum point diode D2 conducts. So each of the diode is conducting 50 times in 1 second, and the question is the diode D1 conducts, okay, not the total number of conduction. Total number of conduction would be 50 into 2, that is 100, but the diode D1 is only conducting when it is positive. Right, now 50 Hz means in each second there are 50 highs, 50 lows, and diode D1 is conducting only during highs, so it will be 50 will be the answer. So 50 will be the answer for this question. Okay, not 25 or not 100. 75 is definitely out of the question. Neither half nor double, it will still conduct 50 times. So even though a very simple question, still it is tricky, because most of the students I know, they will answer 100. Okay, but it is not 100, it is 50 only. Now if you again have any doubts, don't forget to mention that in the main comment below, and I will be back with more chapters very soon. Till then, bye. And if you have not yet subscribed to our channel, don't forget to subscribe. I will see you in a future video.